Connecting a delta transformer to a Y system presents several disadvantages. Firstly, neutral imbalance is a significant concern. The Y system inherently requires a neutral point, a feature absent in a delta system. When a delta transformer is connected to a Y system, it introduces an imbalance in the neutral current. This imbalance can manifest in several detrimental ways, including overheating of the transformer itself, voltage distortion on the Y side of the connection, and an increased risk of ground faults within the system. Secondly, increased power losses are another disadvantage. The delta transformer typically exhibits a higher impedance compared to a Y-connected transformer. This higher impedance translates directly into increased power losses during operation. The higher impedance restricts the flow of current, causing more energy to be dissipated as heat, and reducing the overall efficiency of the system. Thirdly, harmonics distortion can arise. The delta transformer, under certain operating conditions, can produce non-sinusoidal waveforms. These waveforms introduce harmonics into the Y system. These harmonics can wreak havoc on sensitive electronic devices connected to the system, potentially causing malfunctions or premature failure. Additionally, the presence of harmonics can lead to excessive heating in motors and generators connected to the Y system, shortening their lifespan and reducing their efficiency. Fourthly, voltage instability can become a problem, particularly when the electrical load is unbalanced. An unbalanced load means that the current flowing through each of the three phases of the Y system is not equal. A delta transformer connected to such a system can exacerbate voltage fluctuations on the Y side. These voltage fluctuations can be disruptive to equipment connected to the system, potentially causing them to operate erratically or even shut down. Fifthly, grounding issues can become complex. The lack of a neutral point in the delta system makes it challenging to properly ground the Y system. Adequate grounding is crucial for safety, as it provides a path for fault currents to flow, allowing protective devices to trip and disconnect the circuit. Without proper grounding, safety hazards such as electrical shock can arise, and interference issues with sensitive electronic equipment can become more prevalent. Sixthly, transformer rating limitations exist. Delta-connected transformers are generally rated for lower voltages compared to Y-connected transformers. This difference in voltage rating can restrict their applicability in certain power systems where higher voltages are required. Seventhly, efficiency concerns are noteworthy. Delta-connected transformers generally exhibit lower efficiency compared to Y-connected transformers, especially when operating under uneven load conditions. Uneven loading refers to a situation where the amount of current flowing through each of the three phases of the transformer is not equal. This imbalance can lead to increased losses and reduced efficiency in delta-connected transformers. Eighthly, cost considerations come into play. Delta-connected transformers can be more expensive to manufacture than Y-connected transformers. This higher cost stems from their more complex design and the additional materials required for their construction. Ninthly, limited use cases should be acknowledged. Delta to Y connections are generally not recommended for general-purpose applications. The potential problems and inefficiencies associated with this type of connection outweigh the benefits in most typical scenarios.